Hello everyone. This is our submission for the mini project 2, problem 2 for the course CS771. And in this presentation, we'll be presenting the paper Deja Vu, Continual Model Generation for Unseen Domains. We are Team RASNA and welcome to our presentation. So the main problem that has been addressed in the paper is with respect to the problem of handling unseen domains when we encounter new data for training our models. Now, these deep learning models face a big challenge when the data changes suddenly. This is a common problem during what we call as the unfamiliar period. That is the time when the model hasn't yet adapted to these new domain shifts. Or this is the period before or during the training phase when the model actually sees the unseen domains. So our goal is make models more adaptable during the transition phase so that they can handle changes reliably and still perform well after training. So this entire problem has been formulated as the continual domain shift learning problem, which requires machine learning models to continuously adapt to changing unlabeled target domains while ensuring that they do not lose their ability to perform well on previously seen or future domains. This balance is crucial yet difficult to achieve. The main challenge lies in maintaining strong performance during what we call as the unfamiliar period. And to tackle this, the paper proposes the RAT-P framework, which is an innovative solution that focuses on three key objectives. The first one being the target domain generalization, that is TDG, which means ensuring the model performs well on new domains before and during the training process. That is the period when the model does not have a lot of exposure to this new unseen domain. Next objective is the target domain adaptation, that is TDA, and it means maintaining good performance immediately after training on these new domains. Good performance means good performance on past data as well, and which refers to the third aspect, that is the forgetting alleviation, which means safeguarding the model's performance on previously encountered domains, even as it learns new ones. So, to achieve these three objectives, the RAT-P framework introduces three core components. First one is the training-free data augmentation, and this component leverages this approach of random mixer, which is a technique to generate diverse data samples. By expanding the data set beyond the training domain, the model achieves better generalization to unseen domains. The second component is the top square pseudo labeling mechanism. Instead of relying on all samples, the mechanism focuses on high confidence predictions, producing more accurate pseudo labels. It ensures the learning process is guided by reliable data points, again enhancing model's performance to some extent. And the third component is the prototype contrastive alignment. This component aligns the domain representations working across TDG, TDA, and FA objectives simultaneously. By harmonizing how the model processes data from different domains, it achieves a balanced adaptation without forgetting prior knowledge. Now, let us talk about the methodology used in the RAT-P framework. The first component of the framework is the random mix-up augmentation, or the RAND-mix component, which plays a pivotal role in enhancing the generalization ability of the model by introducing controlled randomness during the data augmentation. So the main objective of this technique is to create diverse yet meaningful variations into the original dataset. This helps the model generalize better to unseen data while maintaining label consistency. The core method revolves around autoencoders, which is another powerful framework for learning representations of data. It starts with the encoder E, which is built using convolutional layers to extract high level features from the input data, and the decoder, which utilizes transpose convolutional layers, reconstruct these features into an augmented sample. Now, a critical addition to this process is the adaptive instance normalization, or the ADINE, which introduces controlled noise to the data. By doing so, ADINE creates variation in the outputs without losing the essence of the original data. Mathematically, this is represented by the first equation. Phi1 is the Gaussian multiplicative, and the phi2 is the Gaussian additive noise. Next step is the mixing output stage. And in this step, the original sample and the augmented outputs are combined using random weights. These WIs are random weights, again generalized, randomly generated from a distribution. Then the final output is given by this expression, and this output is scaled by a sigmoid function, sigma of x. And the result is a diverse set of augmented data that not only introduces variety, but also retains label consistency with the original samples, which again ensures that the learning process remains accurate. The next component in the RAT-P framework is the top square pseudo labeling mechanism, which solves the problem of generating pseudo labels for unlabeled target domains, which can be particularly important in scenarios where labeled data is scarce. So the first step in this process is the softmax confidence filtering. See, we have to generate centroids for the classes in order to generate pseudo labels. So the first step that we perform is to filter 50% of the samples based on this softmax confidence. So what we do is we basically use our model and we calculate the softmax probabilities for each of the unlabeled samples and select the top 50% based on these values. The next step in this approach is the centroid construction. Now, based on these top 50% shortlisted samples, we construct the class centroids using the softmax probabilities and basically taking the weighted aggregation to form these class centroids using the softmax probabilities. The next step is a second filtering based on the cosine similarities. So once we have the centroids, we perform this another confidence filtering, which involves computing the cosine similarity between each sample's feature vector and the centroids. And by doing this, we identify the top 50% samples that are most similar to each class's centroid. And again, the mathematical expression is given by this equation. And finally, to predict the class labels, we perform a k nearest labels classification. Again, instead of relying on just the centroids, which can be prone to misclassification in overlapping classes, KNN considered the closest samples to each data point. By fitting a KNN model using the selected samples from step 3, we assign pseudo labels to the target domain samples based on their proximity to the nearest neighbors. The pseudo label for a sample X is given by this expression, y equal to KNN of X given F. And again, the result is that we achieve more reliable pseudo labels, and this approach effectively handles the challenge of domain shifts and ensures the model can adapt to new unlabeled data with greater accuracy. So let us talk about the third component of the RATP framework, that is the prototype contrastive alignment. Now, in the paper, it has been shown that the traditional prototype learning may fail in the problem that we are trying to solve, because as we see more data from the target domains, then it may happen that we may diverge from the actual optimal prototype that we are trying to learn for the different classes, which is known as the increase in the adaptivity gap. And prototype contrastive alignment tackles the challenge of adapting to shifting domains without widening the adaptivity gap. Traditional prototype learning struggles, and hence it is a better alternative. So, how do we do PCA? Firstly, linear layer prototypes use classifier neuron weights as prototypes. This approach ties prototypes directly to decision boundaries, making them robust. Built on diverse augmented data, these prototypes prepare the model for unseen domains while reducing the adaptivity gap. Next is the contrastive comparison, which aligns same class samples across domains for consistency, and it uses negative samples to sharpen distinction between classes. This ensures strong intra-class alignment while maintaining intra-class separation as well. And finally, the process of knowledge distillation transfers insights from earlier models to prevent forgetting. By preserving key knowledge, PCA ensures model performance well on both new and previously seen domains. Let us talk about some of the experimental results that they have provided in the paper. We clearly observe that the RATP approach is quite a promising approach in terms of solving the CDSL problem. RATP achieves significant improvements in target domain generalization, outperforming all baselines in every scenario with an average gain of 3.1 to 10.5%. Again, especially in the domain adaptation methods. Now, for the target domain adaptation and forget alleviation, RATP consistently ranks as the best, or again, nearly the best, often surpassing the second best methods. And as shown by the experimental results, RATP delivers robust and reliable performance across varying domain orders. Now, talking about the effectiveness and some of the takeaways from RANDMix, RANDMix no doubt plays a very important role in the RATP framework, as removing it results in a significant drop in the performance. And this underscores its critical contribution to both generalization and adaptation across the domains. The results, as illustrated in the following figure, validate that RANDMix consistently enhances cross-domain performance, showcasing its effectiveness across diverse frameworks. And by generalizing diverse and robust augmentations, RANDMix not only strengthens the adaptability of models, but also establishes itself as a versatile and powerful general augmentation strategy. Now, talking about the effectiveness and takeaways from the T2PL framework, see, pseudo labeling is very important for our task, but not all the techniques are very effective for this task. For example, when the RATP T2PL mechanism is replaced with traditional alternatives like softmax or short, then the framework's performance notably declines. This is because T2PL isn't just another simple pseudo labeling method. It is designed to refine label quality through a combination of confidence based filtering, what we saw earlier, and then taking the centroid driven class alignment approach. This dual approach ensures that only the most reliable and representative samples contribute to the model's learning process. The accompanying results showcase how T2PL outshines traditional methods by not only improving the generalization to unseen domain, but also addressing challenges like class overlap and noisy data. Coming to the effectiveness and takeaways from the third component, that is the PCA. The first thing that we observe is that excluding it from the optimization process significantly impacts performance, and it leaves only cross entropy loss and log its distillation, which is an incomplete training objective. Further, substituting PCA with alternatives like the regular prototype learning or the supervised contrasted learning has also been evaluated. But the results are also similar to what we expect, that these methods fail to match PCA's effectiveness in achieving robust domain alignment. The accompanying figure clearly reinforces this, demonstrating that PCA is indispensable for optimizing domain alignment and enhancing the model's adaptability to shifting environments. We can observe that RATP sets a new benchmark, outperforming the state of the art methods across a wide range of domain adaptation and generalization scenarios such as continual domain adaptation, source free domain adaptation, test time, or online domain adaptation, and both single and multiple domain generalization settings. RATP's innovative contribution to training free data augmentation, accurate pseudo labeling, and robust contrastive alignment provides a unified framework which ensures exceptional adaptability during the unfamiliar period. And it also mitigates catastrophic forgetting and maintains a consistent performance across evolving and dynamic domains. With its holistic and effective design, RACP stands as a transformative solution for tackling the challenges of continual domain shifts. Thank you.